Thanks. So, thank you very much. Thanks for coming on Saturday morning and showing interest in what we're doing here. So, how do I present the work that we're doing in 10 minutes? Well, I usually, I don't. And because of this, if there's one thing that is important for the various aspects of the work that we're doing in my group, then this is spin selection rules. Because in a nutshell, what we are interested in are measurement techniques that allow not only to detect, but also to measure spin states of both electrons and nuclei. And what does measure mean? Well, when I say measure, that means we should be able to, with the biggest possible sensitivity, distinguish eigenstates of different spins. So it's not only about, well, a spin is here, but it's also about the question, what is the orientation of the spin? The spin is, induces in charged particles like electron or nuclei magnetic moments. And these magnetic moments, of course, have an orientation, a direction. And this is what it's all about. Good. So let me give you a brief, or show you a brief cartoon that illustrates kind of the mechanism that we use to measure spins. So the traditional way, some of you may have heard about this, is, well, that you've heard about this actually just 20 minutes ago. The traditional way to measure spins is a magnetic resonance. So Brian talked about this. What that means is you detect radiations that these magnetic dipoles, these little bar magnets, emit. And this works fairly well, as we saw in Brian's talk. If you hyperpolarize this, you can achieve reasonable sensitivities, but what you can never achieve, or at least it has not been achieved, certainly not with nuclear spins, but also not with electron spins, is using this radiation-detected approach to observe single individual spins. And this is what we are trying to achieve. We haven't with the methods that we are using, but we do on a regular basis have sensitivities that are below 100 spins. And that is many, many orders of magnitude better than what you typically get with magnetic resonance. So what do we do? And the answer is we take advantage of spin selection rules that spin states impose on electronic transitions. So what do I mean with electronic transitions? Well, an electronic transition could be what's illustrated here. I have two localized electronic states. I have two electrons in here. They are represented by their spin orientation. And obviously, if they are sufficiently close, then this electron can jump into this one. That would be an electronic transition, and that could, because electrons are charged, this basically represents an electronic current. So you can measure current, and then you measure electronic transition. You can also, for many electronic transitions, measure these by observing radiation that these transitions produce. And when I say radiation, in contrast to the radiation that you detect with magnetic resonance, radiations that electronic transitions in many materials produce have much shorter wavelengths. So that is in the infrared, the visible, or even UV. And photons in that wavelength range can be detected very, very sensitively, so you can very accurately measure these rays. Okay, so what does this now have to do with spin? Well, the thing is, if you have such a transition, and you have a system which is sufficiently weakly spin orbital coupled, so the coupling between the spin states and the electronic wave functions, the orbital functions, are weak enough so that the spin is conserved, then you essentially have a spin selection rule. Spin conserved means, well, obviously when this jumps in here, what you create is, like, hopefully you remember this from chemistry or, well, your undergraduate physics, you better remember it. It's Pauli's principle. And you create a singlet state here. So if you have weak spin orbital coupling and therefore spin conservation, and then, the question then is to what material or condensed matter system does this apply? The answer is, well, spin orbital coupling has something to do with the atomic weight or the weight of the nucleus of these elements. So you look fairly up in the upper periods of the periodic system. So this could be carbon-based materials, or that means organic materials, but also silicon materials. Basically, all known silicon condensed matter morphology can be considered as a material with weak spin orbital coupling. Well, and again, if you have this, then this transition will depend on the mutual orientation, or in other words, the permutation symmetry of the two spins that we have here. So if you have something like this would be an up-down state. If you project this onto a singlet, that is 1/2, so that's a non-vanishing amount, so the transition would be allowed. If you have such a situation, you have an up-up state, and up-up state is also called a triplet plus state. That is orthogonal to the singlet state, so if you project this, then it is 0. And therefore the transition probability is 0 in principle if you have 0 spin orbital coupling, which you never have. For realistic materials, that means that this transition is just much less likely than the singlet transition. Okay, and our particular focus on what we do is, well, we don't look at eigenstates that I just showed, but we also look at coherent superpositions. So we have means, actually we use magnetic resonance not as a measurement method, but we use it as a mean to coherently prepare non-eigenstates. You can call that spin pair wave functions and psi. And well, if you have a psi on such a spin pair, then you would expect that the transition probability depends on the projection of your coherent state onto, again, the permutation anti-symmetry state, in other words, the singlet state. Okay? So, how does this work? Well, let me give you an example. This is a measurement of charge carriers, basically of a current, through a crystalline silicon amorphous silicon semiconductor heterostructure. And you have at the interface of these two materials, because of the different morphologies, you have localized defect states, and the current flows through this interface by jumping in and through these defect states. And now if you measure this current as a function of the magnetic field that is plotted here, so the plot, this axis here represents the current intensity, this represents magnetic field dependency, and then this represents the time scale, the time during your pulse, well, I haven't said anything about the pulse, during, well, the time during which you measure this current. Then what you see is when you apply a microwave pulse that manipulates these spin states by means of magnetic resonance, and I don't want to go into detail, you've learned that magnetic resonance can turn spins. Then what you see is, well, for most of magnetic fields, and I could extend these axes, you see nothing, so there's actually no current response at all. What that means is this current represents actually a current change, so there's a current the whole time, but what this plots here is the change. And there's no change whatsoever, no response to that pulse. But then there's one particular magnetic field, in this case it's 345 millitesla, where you do see a signal, strong signal. Now the longer the pulse is, well, the higher it gets, and it reaches maximum, then minimum, maximum, etc. Obviously this is some sort of decaying oscillations that you see here. And well, what happens here? Well, as you change your magnetic field, there's only one magnetic field that produces the correct Larmor frequencies for the spins to be on resonance with the radiations that you irradiate. And on resonance, then all of a sudden, due to that changing spin state here, all of a sudden the current is modulated. And so the current changes, and again, it reaches the maximum and the minimum. Why does it oscillate? Well, because you are coherently, on this time scale, these lower nanoseconds, that's much faster than the coherence times of these, at least of these particular systems. You nutate your spin up and down and up and down, and as your spins move up and down, the current moves up and down as well. And of course, electronic transition, they move, and at some point the transition takes place. That of course diminishes the size of this, or the ensemble size of the spins that nutate, or the number of spins that coherently nutate is reduced, and this is what leads to the deterioration of this oscillating signal. So that is a direct way, by just measuring a current, to observe spins, how they mutate. Okay, and if you have such an effect, you basically are able to detect, by current measurements, coherent spin motion and the control of coherent spin motions by means of spin-dependent transitions. Okay, and now the question is, what is this good for? Well, I'm not going to go into details, but let me tell you one thing. Again, it was probably very helpful that Brian had his talk before, but because he showed already what kind of the acrobatics that you can do with spin states by using magnetic resonance. So what we are doing is we apply different pulse sequences of magnetic resonant pulses that manipulate our spins back and forth. And now we observe these spins with electric currents, or sometimes also by means of optically detected spin-dependent transitions. And we can do a lot of the experiments that have been done in the past with conventional magnetic resonance. So as I just showed on the past slide, we can see so-called Rabi notations, the spin notation. Once you can do this, you can apply a pulse sequence that can produce so-called spin echoes. So what we do is we irradiate one pulse, another pulse, and then no pulse at all. But in spite of this, there will be at a later time, all of a sudden, this current jump, this brief current signal, and that is due to a spin echo, which leaves its imprint again in the current transients of the material. Then you can do all sorts of experiments. This is a so-called inversion recovery experiment. And also, related to this work is, we can see when there's a sub-ensemble in a given sample, which means if there's let's say one area of the sample where we have spin polarization and hyperpolarization, we can selectively detect these spins with electrically detected magnetic resonance just by choice of the current passes. Obviously, I can only get a signal from areas where a current flows. So if I have an inhomogeneous current distribution, then I get signals from different volume ranges of our material. Aside from this, we do a little bit calculations in order to understand our experiments because they're fairly new and they are not completely theoretically explored, and we do technical development. And then the last slide, and then I'm going to stop. This is kind of the summary of the applications of this. So what is this good for? Of course, this is what I haven't talked about yet. Well, it's good for very sensitive spin measurement. And this is what you need if you want to implement information technology based on spin states. Of course, a spin, as I said, well, as you know probably, the eigenstates of a spin 1/2, there are just two eigenstates of a spin 1/2. So that means you can essentially use it as a bit. You can even use it as a quantum bit, but you could also use it as a classical bit. But if you want to do this for computer technology, you need to be able to read this. And again, magnetic resonance can do it. So, but spin-dependent transition maybe. And then the other aspect is, of course, material spectroscopy. And we do this on inorganic semiconductors, on organic semiconductors, in order to learn something about spin states that influence that influence electric currents. And why is this important? Well, because in a lot of semiconductor materials, defects that deteriorate the quality of these materials are associated with a spin. So if you can couple to this spin to learn something about these defects, you learn something about those systems that make the materials worse than they could be without these defects. And that is simply important for materials research. It gives you input on what the culprits in a material are that diminish the efficiencies of devices such as light-emitting diodes, that means in particular organic light-emitting diodes, but also solar cells. All these devices are, of course, energy transducers. Either they make light, turn light into electricity or vice versa. And you want to do this with the highest possible efficiencies to make the devices good. Okay, and with this being said, I want to acknowledge my group. We have really very productive folks here, and I want to thank them. Unfortunately, no one is here. I suppose they are working working hard. And also, of course, lots and lots of collaborators. I enjoy very much the collaborations outside, but also inside here within the department. A lot of the outputs that we've had would have not been possible without collaborators and the support, of course, which is reasonable as well for this work at this point. Thank you.
Any quick questions for Christoph? Okay, so save them for lunch. All right, now we're moving on to Dunlop.
Well, thank you for the introduction.
Well, if I do an introduction like you did an introduction,
So I have to apologize. I'm really nervous because this is the first talk in my life I've given on a Mac. So if it goes pear-shaped, then I ask you to go pear-shaped. It's got my copy. All right, so I'm going to talk Well, I didn't realize we were supposed to talk about science here, so I'm going to talk about what we do. And well, seeing all these spin pictures and everything, I feel a little sort of exposed. But anyway, what we do is we build, or we take lots of fancy pictures and build labs like this with lasers and press guys like that. But, if you want to find out about the science, come to me later. So these are the folks who work in the lab here. Unfortunately, Manfred's just left. He was lured away by the evil mammon. So I can't compete in terms of salary with the private sector, I'm afraid. But otherwise, yeah, so we have a reasonably active group. And so I won't go into any details with the science we actually do, just to give a very brief overview. We motivate what we do with the general field of plastic electronics and organic electronics. And of course that's, well, everything's organic, isn't it? So you can really motivate pretty much everything, which really makes it exciting because I give my students and postdocs a fair amount of leeway in actually identifying topics to work on, as long as it's organic, which is everything. So we look, for example, with Christoph, and on my own, we've done a lot of work on spin correlations in organic semiconductors. We work a lot, very interdisciplinary, with chemists, organic chemists, who spend years and years and years of their life on 25 to 30 step syntheses, making ridiculously large, incredibly complicated, but very beautiful, novel molecular systems, so-called power electron systems. We're not quite sure what they're used for yet, but we get basically first shot at actually doing physics with them, and so that's a great privilege for us. Likewise, we work on organic and sort of not quite so organic semiconductor nanocrystals, inorganic cadmium telluride, selenide, things like that. We look at the basic physics of these structures. In the ensemble, on the single particle level, we work a lot with metals recently as well, so we looked at and that's what I'm going to be talking about today, how metals can be used to amplify light-matter interaction and focus light to very, very small volumes. And all of this links together in our activities on actual single molecules, so doing physics not with a bulk collection of what we usually experience in the real world, but on the level of the single entity at once. The important thing to note here is that we try to also motivate our work from many different aspects, and I view myself these days as science has got to be interdisciplinary, particularly nanoscience. So a lot of the work we actually do goes in non-traditional physics journals as well. So the chemists, of course, always view me with some skepticism, but I've been trying to reach out to the chemistry department. So have my students. So we do have some interactions with chemistry here and with other chemistry departments as well. Now, I view this as very, very important for students to realize that science is not just your little box you have here, the little lab you have here, but it's actually a lot bigger. And so, for example, I sent all of my students to the ACS, the American Chemical Society meeting, which was rather conveniently located here early on. This year. Not only because it was cheap to do so. So what we're trying to do is we're trying to actually find out what the nanoscale order in nature is. Now this sounds like a very generic question. We're trying to study the shape of objects and learn about functions of these objects. If you start thinking about the way nature works, it's absolutely mind-boggling. And I'm absolutely perplexed that people spend so much time talking about evolution versus creationism, because they're clearly much smarter than I am. I can't even understand how paint dries. It perplexes me watching paint on a wall dry, let alone how that self-organization process would actually lead to something biologically relevant. So we sort of start things on an even more elementary level. We just ask the question, why does matter arrange in a particular way? And how can we possibly ever hope to mimic this? What I'll talk about today is this mundane silver mirror here. Amazing amount of physics going on in this little mirror, and I never want you ever to look in a mirror again and forget that you're a physicist. And so as I say, motivational, you've probably seen this today already, so I'll go into it. Solar cells, plastic flexible devices, displays and the like. This is all very nice, but this is engineering. So the question is, what can the physicist actually contribute to this? The physicist can say, well, an optoelectronic device is made up of lots of single molecules, 10 to the 12 single molecules, but why not just pick out one molecule and ask what goes on inside one of these molecules? So what is a pi molecule? A pi molecule is just a carbon chain chain of carbon atoms with alternating single and double electron bonds. You've all seen this in chemistry before. What can happen is that one of these double bonds can flip over like that, and so if you imagine this double bond flipping to there, flipping to there, flipping to there, what do you get along the wire? Hint? Current. Huh? A ring? A current! Alright, this thing flips and you get a current along the wire, alright? And so this is what we exploit. That's why we use this in optoelectronics. Obviously, nature has used this type of stuff before. This is not purely synthetic. Look at this molecule, you've all eaten it before. It's just beta-carotene. Right? The dye-stuffs of nature based on alternating double and single bonds. Alright, nature knows that if I flip one of these double bonds here, I get electron transport along the wire. We're just using, or sometimes abusing, one of nature's many inventions. And of course, there's the question, well, I draw these pictures on the board, but they're all flat. So how does the form, how does the actual physical shape of the molecule come in, and how does that impact the function? Just think about your egg, you heat it up by a couple of degrees, protein denaturates, and the function, the actual shape, the structure of the material changes completely with very little change in the actual chemistry. That's what we're looking at, the physics of changing the molecular material while the chemistry is maintaining the same. Now, biophysics trends, I used to be able to say this type of stuff before we had biophysicists in the pub, they were shaking their head now, so apologise for the analogy. What would happen if this thing here were bent and twisted? Keep that with you as an idea. So what do? There's a few pictures from our labs. We spend most of the time fixing things and buying stuff. So we've got something for everyone. We've got lots of cryogenics, liquid helium, and if you like speaking voices, lots of liquid nitrogen here, latex for the friends of that, whatever, boxes, everything. And this is our microscopy lab here, so lasers, there's everything, something for everyone. So we've got a super duper probably the most expensive disco in the state of Utah here. We can pick any color we want, and Doug made a nice little movie of this as well, so we can actually speed it up a little bit. It really is pretty nice to look at. And you can actually do some science with it, but I can't talk about that today. So we also have other facilities that are there in INSEC and the campus. So we use the electron microscope quite a bit. You've probably heard about this today already for structuring and for reading. So physics or magic? Last 2 minutes, what I want to say is what actually goes on in terms of physics inside the mirror. When you don't all know fairy tales, when you appear in a mirror, you get something else looking back at you. Now, if this happened to you this morning well, not all of you shaved this morning, but if this happened to you this morning when you appeared in the mirror, you'd have probably had a bit of a shock when you get something else looking back at you. Now, we as physicists, of course, when we appear in the mirror and we see something, we get really bored if we see the same thing coming back. So if we see something different coming back, like this evil spirit coming back, well, that's when we get really excited and start to ask what's going on there. So it does actually happen. This is the guy who invented the standard silver mirror chemical reaction. It's just a reduction of a silver salt in solution, and you make really nice, really smooth silver mirrors. We have a second venture, which actually generates quite a lot of money, is silver coating bottles from the inside. People like that as Christmas decorations. So if you want to buy one, come and see me. And we can coat anything with silver. Just come and see me. So what actually goes on, when you look at these silver mirrors now under an electron microscope, they're not actually smooth. For some reason, nature lets silver grow in particles. Now, there's no astronomers, but anyway, there is some perplexing similarity in the way nature grows structures on nanometer length scales to I don't know what the length scales are here, trillion light years or whatever length scale. My question is just why? And then maybe we can even figure out how this works. There's we know, we all know that there's a lot of physics going on here because we're in the Department of Physics and Astronomy now. We all know this is important. What I want to talk about is that this here is also important. There is an amazing amount of physics in here. What happens? I shine light at these particles here, these nanoparticles in the silver mirror. And these nanoparticles, they act as little antennae. What they do is they actually focus light to tiny, tiny, tiny volumes. Now, when astronomers see this effect, they all say, well, it's dark matter, and it's all clear. And that's why we get here. But when we see this type of effect, it's like, whoa, what the? So we're shining light in this silver mirror, which looks uniform in the far field. And then we look at the reflection, and the reflection is not at all uniform. We're just shining light in this mirror, and you see the reflection, we get little spots which which are like a fraction of a micron in diameter, coming back at us. What on earth is going on here? Well, these nanoparticles act as antennae and focus the light to very small volumes. When you look at the spectrum, you see there's several different components in the spectrum. The first thing that happens is that these nanoparticles actually double the frequency of the incident laser light. They actually double it. It's like blowing on a water bottle, on a Coke bottle or whatever, and when you blow really, really hard on it, you get twice the frequency, twice the fundamental coming back. And you see that, so we get this so-called second harmonic generation, twice the frequency reflecting off this silver mirror, this broad spectrum here as well. So we have a lot of fun with this, and this, just to finish off, is so what we do, our deep space survey in the lab. This is a small fraction of a silver mirror. Anyone know what a ZPC is?
Zettaparsec?
Almost. Zeptoparsec, that's right. One zeptoparsec is about 30 microns. And so if you expand this up to the megaparsecs that our astrophones, whoa, I mean, we would take the age of the universe just to get up to 1 parsec at the present rate in our lab. There's an amazing amount of stuff going on here. Literally every spot is different. And I mean, as I say, we don't understand nature yet on the zeptoparsec level. How can we ever hope to understand it? But anyway. So why is this important? Why are we actually doing this? Well, of course, like all physicists, we're trying to save the world. And we save the world by controlling the light-matter interaction, by focusing light. Seriously, how do you like rubber proposals? By focusing light into very small length scales. So, of course, this used to be important. I hope that you never catch the guy. This used to be really important for homeland security because, of course, you can detect anthrax spores and things like that with it. I use this to explain inhomogeneous broadening. This famous picture of the New York Times. These guys, if they'd used microscopy, they'd have figured out that whoever made this poster here, the bird was hidden in there. This just explains the utility of single particle and single molecule spectroscopy. You can't see it on the apple. Bird from Sesame Street. This was a picture of the New York Times, and for some reason the terrorist, he was just Google somehow on Google, and everyone knows birds gay and evil, which doesn't mean but that's the conspiracy theory. But don't ask me later. This is just explaining the we can use this to trap. No, seriously. Amplified light-matter interaction can allow us to actually identify single molecules at once. At the same time, amplified light-matter interaction, if we don't have as much space as we do in the Utah desert, we can actually focus light down to very small length scales. So, of course, we can solve all of our energy problems with this, and photovoltaics, and you understand me. So, ultimately, what are we trying to do? Of course, again, this is really engineering here. What are we trying to do? We're trying to understand how nature gets from a particular structure to functional. And as I say, I don't think we've come very far yet. We know there's a lot of amazing structure out there. We know there's a lot of amazing function, but so it's a great area to work in because, there's plenty of problems and plenty of answers. We've just got to bring them together. All right. I wasn't done with the quiz docs.
Okay. Thanks, John. The question that you asked us to make sure you have it all working. So now we're Valley Gardeni. We'll hear from Valley.
It's very nice to be the most single guy here. That's the beauty of being academic. We see 3 generations actually. I'm the old generation, there are intermediate by some and so on, and then some young generation. And we all do the same thing, we need students. And we all do the same thing, educate students. And so my talk will be geared to educate students. I have a large group, 2 postdocs and 7 students, and each of them does different things, starting from plasmonics through cancer diagnosis to high pressure chemistry, to femtosecond, picosecond, to speed valves and so on. But today, I want to talk about a single part of my research because a student of mine got a position somewhere else and he will leave in February. And this is a virtue of what I'm doing because students are going everywhere, and I feel like a policeman actually. That means go there, go there, go there. And so people come, and in 4 years you go. And so all the memories and telephone calls and Christmas cards that I get. Okay, in organic solar cells, that's one part of my research, and I collaborate with an industry, actually Tektronix, and they supply me materials, and also we synthesize. Actually, our group, we can start from synthesis, and we do applications like organic solar cells and so on. Everything done in my group. And so, in general, if you look around, we depend on fossil energy a lot, and 80% of our energy comes from fossil. And very little come from photovoltaic, nuclear too, a little bit. We need 13.2 terawatt hour, but it's enormous, and we will need more and more. And you all know the story. The story is that in 1 hour of sun irradiation of the Earth, we can actually potentially do energy or give energy to the Earth for 1 year. And so there are all kinds of photovoltaic effects. One is crystalline silicon, but it's quite expensive. The other one is amorphous silicon. It's not as expensive as crystalline, but those are not soft material. And when you add up the cost, it's 6 kilowatt per hour, $6 per kilowatt hour. But organic solar cell, at the moment, we want to shoot for 0.3 kilowatt per hour, $0.3 per kilowatt hour. And this is our goal for a few, not only us, but DOE too. Let me define what is photovoltaic effect for those of you that do not know. Is the ability to generate voltage from sunlight or other light. And you got light in and you get voltage out. And for sunlight, it's absorbed by a semiconductor, and the semiconductor generates electrons and holes. And there's an electric field. The electron go one way, the hole goes another way, and you collect them, and you create photovoltaic. And for those of you that know, electron charge is 10 minus 19, so you have to collect a lot in order to get 1 volt. So for photovoltaic, both charges contribute to the photocurrent, and this is very important. Both charges can be collected. And so in general, when you shine light, everybody knows what is a diode. An IV characteristic of a diode, when you shine light, you see that the IV characteristic goes down. And so it's the same IV characteristic as before, except that it's shifted by the current that you generate by light. And there are several definitions, and using this definition, you can calculate how much of the sunlight you can transform. And usually, this is a very useful equation, because P in of the sunlight is 100 milliwatt per centimeter square, so it's 100 here. So all the numbers, if you multiply them, you can get in percentage directly. And so what we have right now with organic photovoltaic, we have a maximum of 6.5% of recall. But in say, crystalline silicon is maybe 25 to 30%, but it's very expensive. So thank you very much, John, for introducing the organic semiconductor. For me, for us, it's like if you look at it, it's like spaghetti on a plate, and actually it's very close to lunchtime. We are very hungry. So originally, when maybe 17 years ago, the organic electronics started with organic light emitting diodes, and this is composed of 2 electrons, cathode and anode, and in between there is a polymer which is active material, and you inject electrons and hole, you get light out. But nowadays we are interested in the opposite reaction. This is an organic light emitting diode. You inject electron and hole, get light out. But at the same time, or the same construction, you can get light in and generate voltage. So we are interested in that, but the construction is the same. It's similar. So my group, we do both, organic light emitting diode and we put magnetic field, and this is one part of my group. And we have a postdoc that is interested very much on that. And the other part of the group, we construct organic photovoltaic, and we electronically measure the kind of efficiency we want to increase it. Particularly, we have two organic semiconductors that we love and appreciate. One is called the polymer. Polypropylene polymer was invented several years ago and has a very large mobility. The other one, and this is a donor. An acceptor is a fullerene and was invented maybe 15 years ago. On polymer, Nobel Prize in chemistry was given in 2000. For fullerene, Nobel Prize was given before. But if you put them together, this is what happens. You excite the polymer and you create an exciton that means bound electron hole, and for some, the electron can jump into the acceptor, which is a fullerene. This is a polymer, it's a fullerene, and the hole stays behind. And now, if you have the electron field, the hole goes one way and the electron goes the other way. If you ask me, you can do the opposite. You can excite the fullerene, and then the hole goes to the polymer, so it's completely symmetric, except that the fullerene doesn't have the block. And so what we want, this is a bilayer device. We want a donor to be here, an acceptor to be here, the electron goes in this way, the hole goes in this way, so it's just the opposite than in organic light emitting diode. And the more that we collect, the better, because we increase the efficiency. Except with bilayer, I'm going to tell you that exciton move very little, so only 10 nanometer here, exciton may leave. So most of the exciton that you excite here apparently disappear, and they don't create any photocurrent. And so what we do in organic photovoltaic, we put them in together in a blend. So this is nanotechnology already, and John Newton told you about it a lot. But for us, it's a blend that we shine light on it, and naturally, the electrons and hole find ways to go to the opposite electrons. And so this is what happens in a blend that we call bulk heterostructure. This part, this macaroni, is a polymer. This part is a small fullerene, and we shine light. Mostly light is absorbed in the polymer, and then the exciton dissociates into electron and the hole. The hole goes this way, and the hole goes this way to the other, and the electron go from one fullerene to the other to the cathode. So all of this is a lot of material science, chemistry, nanotechnology, nanoimaging, and actually understanding what's going on. It's very labyrinth. And so, for example, I give you several examples of achievement in my book. Jan was a student, now she's a faculty member in Florida, and actually she would be the faculty member that will employ the student that now goes in February to Florida. And this is highly characteristic of an organic photovoltaic. Before we do something with it, and we bake it. At that time it was new, in 2002, we bake it. I call it bake, of course other people call it anneal, but it's the same thing. We put it in high temperature for 10 minutes, and then the electron hole naturally find better ways to arrive to the electrons. And so we increase the efficiency by a factor maybe 5 to so. However, our biggest problem in organic photovoltaic right now is a mismatch between the spectrum of the sun spectrum. This is the sun flux on Earth. Disregard was some absorption due to water, and so our absorption for organic photovoltaic is start at 600 in the visible band, and we want to extend it to 1,000. And so we have to synthesize new polymers, And I want to add that we have the chemists and synthesize for us all kinds of materials. This is very important to be self-contained in this business. And we want to go to the infrared. So we have now polymers that are infrared, that absorb the infrared. We want to put it together with fullerenes and to go to another step in organic photovoltaic. We have problems with degradation that we want to measure, and there are several aspects now or technique to measure the degradation in our samples. Moreover, we have other goal to replace. There's a transparent electrode called IPO, which is indium tin oxide. And because of many photovoltaic, indium becomes very scarce. So we want to change the electrode to other electrodes that are, for example, nanotube electrodes, rather than indium tin oxide. So this is what we do in our group. And finally, there is some physics, of course. And the most dramatic physics in photovoltaic right now is the following. All of us know from textbook that one photon can generate one electron and one hole. However, 5 years ago, somebody came with the idea that maybe if you generate electron holes that are energetic enough, then by cascading down, there is a process that I won't mention, but by scattering other electrons, you can generate more electrons and holes. So actually, from one photon, you can generate maybe, well, they say up to 5 or 6 electrons holes. This would be wonderful, because then you can think about it. If you have 6% quantum efficiency, if you generate out of one photon 2 electrons and holes, then you can jump to 12. Ideally, it's not like that, but ideally. So this is the physics that we want to pursue. In organic, this is generating of triplets. So now we have triplets that are bound electron hole for each exciton that we create, generate 2 triplets. And now what to do with these triplets? How can we multiply our efficiency using these triplets? In general, my group activity in organic research is synthesis. One can learn synthesis of different molecules, fabrication of organic solar cells from polymers. We can put additive, all kind of radical spins, magnetic field, and so on to improve the power conversion efficiency. We measure transfer property. Of course, we have to patent it, license, ties with companies. So all of this, if you are a good student, you can enjoy. However, things that I'll provide for an RA, I need an RA right now because the student leaves in February. I need some kind of overlap. And so I have an RA position starting immediately, training by a senior graduate student, generous budget for research. We have Monday morning group meeting of maybe 11 to 12 people, everyone. Each week we talk about different aspects of our research. Supervision is tight, the experienced supervisor like me and 2 postdocs that we have. End publication, don't worry about it, and actually helping funding post-graduation job. However, I need also from you, the students, to put something in. The student that I ideally want to be ambitious, enthusiastic to work hard, night and sometimes like we work now in weekends. Fire in his bones, otherwise we cannot arrive to anything. Curiosity curiosity to learn, very good hands, understanding, obedient but not shy, and adventurous. That's the most important. Not afraid to explore. If you think that you have all of this, you can come to me now.
Right behind,
brought me to the stage.
we're running behind, so please save your questions for Valerie for lunch. And I know that we can all smell pizza. We have only 2 more talks. Everybody's hungry, but please give your undivided attention to these last 2 talks because it'd be horrible if we had to shortchange these stuff. Okay, so let's see, Andre. Yeah, I know, but where is put it in here. Yeah. Okay, I guess that's the first time we're doing this meeting, and I guess everybody is sort of in a way of finding how it's supposed to go. And I took so-called minimize John's approach. I'm not going to talk much about kind of science behind what I'm doing, but more actually on sort of on practical level, what you're going to do in my lab, and maybe what projects we will do if you decide to go to my lab. So it's kind of very on few students. So if I basically use the name for my lab, it's like a scale transport word, or scale transfer. So why we're interested in scale physics? It's kind of obvious because we have this huge problem in semiconductor industries that if we don't scale transistors and other elements, then eventually we should come to a stage when current models of these devices are not going to work. So actually we need to develop some knowledge, or better yet some new technologies that provide a grounds for this future downscaling of semiconductor devices. But of course, to do that, we have to also understand the physics that appears at this light, at this scale. And actually, there is a lot of new physics that derives when we go to the nanoscale. It's to change the size, you see that just you have the same branch of phenomena, but that's not actually the case. So you kind of count different things like appearance of the charge discreteness, appearance of quantum time. If you change the size of the system, it's smaller than some spin flip rate, then you see different spin-dependent effects. And if you want to study these effects at some laboratory setting, you need to go to low temperatures because temperature usually kind of kill all interest in physics. So basically, that's kind of overall scale characterization. But what system we studied? And I kind of sit down yesterday and look at what, and actually we kind of study the system right away at all dimensional levels. So basically we study zero-dimensional objects, that is molecules and short coherent wires. We study one-dimensional objects, that is superconducting wires, magnetic nanowires, and carbon nanotubes. And also we study two-dimensional objects, which is superconducting tubes. And the future basically in this kind of field, you don't worry just about an object, because that's kind of quantum mechanics. It's also important to understand how your object interacts with surroundings and what makes quantum and not classical. And to study this, you actually have to proceed and basically make some kind of hybrid system that include both effects of object and electrodes and some other more fancy surroundings. So what we do? Of course, we don't do everything, but by saying we do everything, I mean just to sort of complete this project, you have to go through a quite large number of steps. And of course, transport doesn't seem like complicated thing, and kind of, you might say this is just low temperature, high field, but this is still more or less relative measurements. So basically, the expertise and the difficulty mainly lie in the field of fabrication, new, interesting structure and devices. And to do that, quite fortunately, after some years, I mean collectively, me and department at the university, kind of actually very wide range of tools that will be used for fabrication of these devices. So basically, in our case, we have in-lab material deposition facilities, and we have if you do that, you will learn a lot about high vacuum techniques. We have in our department sample imaging and electron beam lithography facilities, so you can actually make very small structures. And then my students kind of use very actively the facilities that are available at the Department of Electrical Engineering. So basically, you kind of go through this. There's the one in the middle. So you kind of go through this procedure and you think you kind of do fundamental physics, but in fact, you acquire very good preparation for basically work in industry. So that's all this set of these tools is something that is actively used in semiconductor.
So once you've done with kind of this sample fabrication stuff, you have basically measurements that are going on in our laboratory. So that is low temperature measurements because we need to get rid of these thermal effects. But also doing this, you kind of develop skill that are related to basically data acquisition. We actively use LabVIEW programming and for that. And sometimes we also do small electronic circuits just to solve some more specialized equations. So that is sort of a key part. And now we sort of develop more advanced technique that is noise measurements. And in the near future, if we have fun, we also will have and try to do more sort of faster data acquisition systems. And of course, there is third part, which is data analysis, and maybe the difference between, say, me and probably Christoph, not Christoph, but probably John and Val, is that when you do transport, you actually go ahead and do very detailed comparison with series. So you actually have to go sort of deep, sit down, and maybe work with series. Sometimes it's lengthy complicated equations, and often what is required is sort of quantitative comparison. Quantitative, I mean, like you get numbers, you get some detailed stuff. So data analysis is also important and time-demanding part of this kind of projects. So let me maybe show what we have in our lab. So we, this is basically splattering apparatus, so we can grow our own materials here. We've got this scanning electron microscope that allows us to look at the sample, and also this is also fabrication tool that allows us to make small structures. This is helium-3 cryo stuff. So basically we work at this lower temperatures. There is option to include high frequency measurements, and this. And just maybe let me briefly to explain two main methods that we are currently using to produce our samples. So one of them is a kind of neat technique that allows us to make very thin nanowires, and it has fancy name, molecular templating technique. So in this case, it is shown for the case of carbon nanotubes. So you kind of start with this sort of structure, then we drop carbon nanotubes, which are very thin molecules with diameter about 1 nanometer. And so some of these nanotubes actually drop across the trench. And later, in the second step of the deposition, you actually, in the second step of fabrication, you deposit material all over this structure, and what you end up given is a picture that looks like that. So basically we have this trench. You see a lot of carbon nanotubes flying around, but some of them basically cross the trench, and this is the future wire. And because the wire can be seen, the wire itself has a diameter of about the size of the carbon nanotube, so you can potentially make wires in the range of say down to 5 nanometers. So that is some example of the wires that have been fabricated in our laboratory. So that is vanadium nanowire. This is nanowire made of magnetic materials. What is important that with this method we actually fabricate wires on sort of basically on the level of the world record units.
What's the scale on the method? Sorry,
One micro. This is not otherwise you'd be surprised. So and also it's material science of these devices kind of it depends on the kind of materials that we are using. For example, here for magnetic materials we make both sort of granular wires and more or less continuous wires, and both of these devices can be useful for different physical problems. Next, this is just another tool that is available right now, that is called electron beam lithography, that also allows to make very thin wires, but they are sort of made more granular sizes. So our whole picture is world record achievement in this technique, and what we are doing now is something in the range of 30-40 nanometers, and our goal to get to the range of 15-20 nanometers, and then we have a broad range of physical problems that we may solve with this technique. So what problems are these? So the main area, or main current area of our research is quantum phase transition. So if you look at this picture, it shows you what happens if you take very thin superconducting film and continuously change its signal. So basically, initially you see some sort of insulating behavior, resistance increases with decreasing temperature, but then you have so-called critical point. And those of you who are taking my statistical mechanics class know that at the critical point we have phase transition. But normal phase transition occurs at basically at some temperature, but here we have transition at zero temperature. So we have transition from insulating state to superconducting state. And this point is very peculiar because ideally at zero temperature we have a jump from infinite resistance basically to zero resistance. Interesting thing about this kind of field is people now actually found some profound mathematical connection between this mathematical description of this kind of phase transition and something in string theory. So basically you may look at this point as the point from which universe starts. And that's going to be very exciting because maybe doing this low temperature stuff we actually looking at very profound fundamental questions. So our immediate two projects that are in our laboratory right now is the critical regime of this type that occurs in superconducting nanowires, and also we want to study how understand how magnetic impurities affect this behavior. The other projects that are available in this direction is basically the very interesting question is if you have quantum mechanical system, then what you want to do, ideally, you want to kind of disconnect it from environment. And people who are working on quantum computing, they're really trying to achieve this by different kind of means. But as the other, complementary question is what happens to quantum mechanical system if you start to control this environment. And basically what you want to study how quantum system sort of loses its quantum phenomena and translates into the classical logic. And that is something that can be sort of done if you have a way to control this environment, and I have some ideas of how we can actually do that. The other project is basically magnetic nanoscale devices. So basically what I studied so far is homogeneous wires, but interesting thing is that if you deposit material on top of carbon nanotube, it actually not always produces this uniform coverage. What often happens is it forms these kind of small metallic clusters. So, of course, you may consider this is sort of not pleasant defect, but at the same time, this could be very interesting method of creating and at the same time studying very small magnetic objects. So basically, the idea is here is because nanotube is so small, we can make magnetic clusters in the size, they will be too large here, but let's say 5 nanometers. And again, this is something that will be very hard to achieve. But then you can also make device in which your carbon nanotubes, which can be also conducted, can be used as a basically means of measuring the transport of carbon nanotube. You can actually check and say something about the magnetism of your magnetic particle. So that's kind of complicated device that involves both magnetism and physics of our carbon nanotubes. Unfortunately, here in our department we have an expertise in carbon nanotube growth, and likes with Jordan Gartner, and we started some collaboration in this direction. And the final project that we are sort of available and that we are doing is transport of electronic noise in self-assembled monomers. So in this area, in this project, which is related to the field of molecular electronics, basically there are two. The goal is to substitute silicon in the transistor by a molecule, ideally by a single molecule, but more realistically by a collection of molecules. And perhaps the biggest problem in the field of molecular electronics is sort of irreproducibility. So you don't know, you basically how to create a device is the same properties. And one of the methods actually to look at this property is just detecting noise spectrum, because noise spectrum may contain information about the defects in the system. So that's one part of this project. And the other is again related to the problem in this field, because people can easily make, let's say, dyes these molecules. But what we need to have is also a sort of 3-electron device in which you have both drain, source, but also gate to control the currents in your system. And that is a picture of the proposed device that can actually perform this structure. So you have 2 electrodes, you have the layer of nanotubes, you have a gate. So that's another interesting project that involves both computation and measurement. So I would like to reiterate. So in this, in my group, we will very likely deal with very fundamental questions, but the range of different tools that we are going to use is broad and prepare you for almost anything you want to do in the future. So if you want to work for my students, so that's what they are, and you may ask them more. This will not be principle.
We're running behind, so let's save questions for pizza. So our last speaker is Clayton Williams.
Thanks. So I have the enviable position to be between you and lunch. So I'll keep this 10 minutes. So my group is focused on what we might call true atomic or true nanometer scale characterization of materials, electronic properties. And I'd like to point out that the word nanometer scale is a somewhat abused word, since nanometers exist anywhere from 1 to 999 nanometers, which is approximately a micron. Everybody who wants to get some funding or attract a little bit of attention uses the word nanometer scale. And what I'm going to describe for you today is some studies that we're interested in doing and that we have done, but is really on a sub 1 nanometer scale. And it's a somewhat different domain than the larger nanometer scale is oftentimes discussed. We're interested in point defects in dielectrics and in semiconductors, and maybe eventually in some organic materials, and in looking at those on an atomic scale. And I'll motivate why defects in dielectrics are interesting in the next slide. We're also interested in true nanometer scale, few nanometer scale properties of, say, nanorods, nanoclusters in molecules. We're also interested in collaboration with Christoph in demonstrating the ability to detect a single spin with atomic spatial resolution. And we're also interested in using the approach that we've developed in the last few years to do atomic scale lithography. So why study dielectric surfaces on a nanometer scale? Well, first of all, there's dielectrics are insulating materials, so they have not received the same attention as semiconductors on an atomic scale because they don't conduct. And our group in the last 7 years has developed the ability to actually perform tumbling measurements to and from the scanning probe tip to a completely non-conducting surface. And it opens up for perhaps the first time characterizing some surface states, single dangling bonds at a non-conducting surface on dielectric surfaces like glass or other kinds of materials, and to look and measure directly the physical and chemical properties of those individual states. Electronic trap states are important actually in dielectrics in all electronic devices. Every field effect transistor that you have in your computer memory or flash memory depends critically on a gate dielectric. which is between the gate and the channel. And trap states in the little atomic defects in these gate dielectrics can destroy those devices, and people work very hard to make sure that they are either not there or they're at a small enough number that they do not influence the device performance. And of course, when we talk about flash memory and you store these ones and zeros in these charge states, these trap states actually are the things that cause those states to leak out. And when you have flash that has a certain scale, you store maybe 100 electrons in these little charge storage elements. As you continue to shrink them down, you get to smaller and smaller numbers of electrons that are stored, and the leakage of problems associated with just a few traps can be enough to kill it. And so our efforts are aimed at really trying to characterize these traps on an atomic scale. And with the spin capability, we may be able to actually do a chemical identification using ESR to identify individual traps and trap distributions in a dielectric surface. And these traps also represent the ultimate limit of a quantum dot. So the fact that you can put an electron into a trap state, and because of its confinement, even at room temperature, some of its quantum properties are maintained, and it is an interesting system that you can think about doing maybe some kind of quantum information analysis with. We're also interested in molecules and quantum dots and nanoclusters that are sitting on dielectric surfaces. In this first picture, I showed you, this is actually an STM image of a quantum corral. It's, I think these are iron atoms on a copper surface, and the STM, which is so good at seeing things on an atomic scale, shows each of these iron atoms as a single peak here, and you actually see some quantum interference associated with the surface states of the copper. This technique is so useful on conducting surfaces, either semiconducting or metallic surfaces. We are now doing similar kinds of images on completely non-conducting. So this is an image of trap states on actually hafnium silicate, which is a dielectric. So just as a quick illustration, what are these electronic defects, say in silicon dioxide, that has been the primary gate material in silicon devices for about 40 years? Well, there are several types of defects. There's traps that are constantly charged. There's traps that are near the interface, and traps that exchange charge with the bulk. And in many cases, they are, probably Christoph talked about these centers, PV centers, which are basically just a silicon that is not bonded to an oxygen, and there's this one electron in the negative bond there. So that's a state that allows an additional electron to come into that, and that electron remains is basically a trap there, and it shifts the properties of the devices. And there's a bulk defect called E prime center, which also is basically an oxygen vacancy, and the silicon the electron of the silicon atom is basically, there's only one electron there, and it can accept an additional electron. So these are true atomic scale defects that have very important and interesting properties. Well, we've developed this method of what we call single electron tumbling force microscope. It's like an STM that is capable of tumbling just one electron from the probe tip to the surface, or a state in the surface, and then you can actually pull that electron back to the tip. And so you shuttle the electron to and from these atomic states because the electrons can't leak away into other states. And what you see here are a bunch of measurements where we're scanning the probe toward the surface. If there's a state there, we actually see these little steps, which is just one electron tumbling into that state. And we can do this any time of day, as long as the system's working. I was going to say day or night, but that's really not true. Here's just two pictures. Here's an electron that we put on the surface intentionally, and then we've taken it off, and we see that the surface, the electron is gone. So this is a single electron kind of control. We also can use that same technique to actually measure the energy of a particular trap state. So this is an energy diagram, and this is the probe tip with the Fermi energy up to some point. It's metallic. There's a gap. This is the vacuum, and then this is the SR2 with its 9-volt electron volt gap here. Let's say there's a state that's sitting somewhere in the middle of the gap, and because the gap is so large, that electron, if you put one in there, it doesn't have any place to go. As we scan the Fermi level from below that state to above the state, the state actually is initially unoccupied, it then becomes intermittently occupied. The electron actually telegraphs back and forth between the state and the tip, and then it becomes filled, and then if you ramp the voltage back down through the state, it telegraphs and then it's empty. And so we have this ability to control with atomic resolution the occupancy of the state. Okay, I've got 2 minutes left, so dynamic tunneling is basically a way to not only statically put the electron in or take it out, but actually to shuttle it to and from the state, which helps us to do imaging. And this allows us to image completely non-conducting surface, and this is a 20 nanometer by 20 nanometer image, and each one of these is a single defect or trap state in which we can put shuttle electron to and from. The interesting thing about this is because the tunneling depends so critically on the gap between tip and the state, we can actually do 3-dimensional depth profiling, because as we lift the tip up, some of the states start to disappear because you can't reach them by tunneling. So this is actually an image taken, and then a second image taken with the tip at 1 inch from increased height, in other words, further away from the states. And what you see is that 2 of these states, this one and this one, actually have dropped out of the image, and the others have actually become a little bit smaller in diameter. And that effect is associated with the fact that when you have a state that is deeper, you can only tunnel to it from the very end of the tip, whereas if it's closer, you can actually tunnel not only from the end, but from some finite radius of the tip, and that changes the apparent size of the image. We've also looked at, this is actually sort of nanorod that has come from John Lupton's group, and the interesting thing is that because of our spatial resolution, this nanorod is made of cadmium selenide and cadmium sulfide. When we tunnel to one place, we see a different gap than the other. And even though it's only 6 nanometers long, you can see the different band gap in this region versus this region. Finally, this is actually a movie, but because this is a PDF file, we can't see it. But there's some beautiful work by a guy named Robert Wilco, who has shown the ability to actually bring an STM down and actually desorb a single hydrogen on a surface that is a silicon sample that has been hydrogen terminated on the surface. You can desorb this with atomic resolution. And each time you absorb it, you create a dangling bond, which actually is an electronic state. And he has created one here, initially one, and this would have been shown in the movie. He then creates a second one, and these 2 dangling bonds now actually interact, and electrons can tunnel between the 2. So it's like an artificial molecule. And then he puts an additional dangling bond over here, and because of the charge of this, you actually can see that this is bright and this is dark. And so he's influencing the quantum state of these 2 coupled electrons with an initial charge, all on a scale. This is something like, well, this is a total of 3 nanometers, so this whole thing is about 2 to 1.5 nanometers. So to conclude, our group is interested in playing with electrons at dielectric surfaces, but more than playing, we want to use these methods to actually study the electronic properties of single atomic states and bonds and defects, and to explore the electronic structure of those things, and then to actually create and use these defects to do interesting physics. So appreciate your attention.
Thank you. Okay, so I prepared a 30-minute wrap-up. I guess we'll probably skip it. But I did want to say I hope this was useful for the students, for you all that are looking for advisors. I thought it was very interesting for myself. It's great to get an overview of what all is going on in the department. If you have any suggestions, though, for next year, because we'll run it next year, if I think it seemed like it was reasonably active, and so please send me your emails, send me some emails on suggestions on how to improve it. or just grab me in the hall and let me know. Okay? So pizza awaits outside. Let's thank all the speakers again.